Excellent. Right. Morning, everybody. So we'll just get this screen up. And now, hopefully, everybody can see a slide that says BGP metrics. Yep. So I'll just do this. Just bear with us a second. Right. So as I say, with a bit of luck, you'll all be able to see this BGP metrics screen. And it says here, just bear with us a second. As Holly says, my name's Richard, so I've come across BGP once or twice, so we'll see what can happen. I wouldn't say this is a deep dive, as the expression is, into BGP, but it's certainly not a brief overview either. So we'll see what it has to say. You will find that at times, especially in the first few slides, or it will look as though I'm going off at a tangent. I'm not. Yeah, it is to gradually build up to a point. You'll see what I mean. I also have a topology that I'll be showing you soon, so you can see what effect BGP has. And I've got a blank PowerPoint presentation that I'll use for drawing, again, to try and prove a point. We have to get a few points across. Yeah, I tend to use that quite a lot. I will warn you, my drawing is not of the Picasso type standard, but it should do to prove a point. Okay, so anyhow, here we go then. So this is the first slide, as it says, BGP metrics, whoopie-doo. It's talking about, we will be talking about how BGP, Border Gateway Protocol, it's version 4 that we're using, how it goes about selecting the best path to reach destinations. And then the other little footnote there is, it talks about local preference, and it talks about a thing called a MED, a multi-exit discriminator. These, the local preferences and the MED, the multi-exit discriminator, also known as the metric, are two of the attributes that BGP uses. When I say BGP attributes, I also mean BGP metrics. So an attribute basically is a metric, if you like. There are quite a few of them, and you will see them shortly. Okay, so with that in mind, that's it. So I'll go on to the next slide. Okay, this is talking about internet working and whoopie-doo. You can see here, we've got this, for those who are not familiar with these symbols, this one here with the arrows is a router, yeah, as it says, and it's also known as a TCP/IP gateway. Again, whoopie-doo. What we've got here is hanging off this router. This is not especially relevant, but we've got a broadcast domain here. Fine. We've got another broadcast domain, sorry, in here. Oops. That had to happen. Right, try again. Got another broadcast domain in here. Okay, you can see the addressing schemes 10.1.1.1, 10.1.1.2, 10.1.1.3. Again, not especially desperately important, but just be aware that this is a broadcast domain. This is a second broadcast domain, a third broadcast domain here. I suppose if we was to say that this cloud represents the internet, this is probably more important, but we'll leave it at that for the moment. And then finally, we've got another broadcast domain here. So jumping back a slide, as it were, we are talking about internet working, all of these broadcast domains together. Yeah, so there's 1, 2, 3, 4 broadcast domains, and there they are with their addressing schemes in place. Fantastic. So far, so good. This is more like it, talking about routing tables. Routing comprises of using, it can be static, where we can set up the routes ourselves for data to reach a destination, or we can use what's called an IGP, an interior gateway protocol. What I'm just going to do now is talk about IGPs for a few minutes because it is relevant. I quite appreciate if I talk about RIP, Routed Information Protocol, which I will for a very short period of time. There might be some of you think, oh my goodness me, why are we talking about RIP? I thought this was BGP. It is, just bear with me on that. So I will mention RIP, I will mention OSPF, and that will be that. All right. But what we've got in here, 3 routers, of course, and we can see here, if I pick on this one just at the end, right, we've got a routing table here that says to get the destination, to get to 172.16.0.0 here, the data, the updates would need to go to the next hop of 192.168.1.1. Well, as you can see, there's 1.2 here on this interface and 1.1 on this interface here. Again, whoopie-doo. Then the middle router has got a destination of 172.16.0.0 down here. The next hop for this device is 10.1.1.2 with a metric of 1. So what? On the final device here, the destination is 172.16.0.0. It is a local network, it is indeed, so there are no hops involved, and consequently there is no metric because the thing is plugged in, all right? But just be aware that all the routing protocols, RIP, OSPF, ISIS, EIGRP, etc., will calculate this route and they will allocate a metric, all right? Which is one of the things why I want to hit on it with the drawing, all right? So hopefully everybody is quite happy with that. That is quite fundamental to routing, okay? Within there, these are the routing protocols. These, you've got RIP, Routed Information Protocol, OSPF, Open Shortest Path First, ISIS, Integrated System to Integrated System, and there's BGP, Border Gateway Protocol. The first thing to realize is that RIP, OSPF, ISIS collectively are called IGPs, Interior Gateway Protocols. Then there is BGP, Border Gateway Protocol. This is an EGP, an Exterior Gateway Protocol. What does that mean? Well, hopefully, now this is where the fun and games will start, chaps. I'm going to load up my PowerPoint. So just bear with me. And you should have a blank PowerPoint presentation in front of you now. Okay. And what I'm going to do now is this, right? I am going to draw a router. That is a router. That is another router. And here, I'm just encompassing it in something, and I'll put an internal device in here. Fine. I will connect that with, we'll say, a cable. Fine. That will go into here. That will go into here. Whoopie-doo. Then I'm going to draw another thing over here. Another thing over here. And again, just encompass it, encapsulate it, dare I say. Draw another router here. Da, 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 da. I do hope everybody can hear me. So, right, that'll do. So we've got these three systems here. There we go. There's no bearing on the number of devices, but these are all routers. This is a router A, this is a router B, this is a router C, etc. Right, now the point is, and this is the first important hit, or at least it will be when I've finished drawing these connections. Right, this system here, just bear with us. Yeah, this system here is what they call an autonomous system, an AS, right? An autonomous system means a network or a series of networks that are under a common admin policy, yeah? So This is also an AS, or it will be when I get some ink in my pen. This is also an autonomous system, as indeed is this. So we have 3 autonomous systems here. We will say all of these ASs are identified by an AS number. Okay, I'll write it like that because it saves me ink and saves you reading my writing. This can be a 16 or a 32-bit number. I'll work with the 16-bit ones. 2 to the 16th is 65,536, as I'm sure you're aware. 36, so it goes from 0 to 65535. Fine. Within that, the range 0 to 64511, whoops, 64511, they are public ASs, and 64512 to 65535, 65535 are private. Fine. The private ones are not allowed on the internet. All right. The public ones are. So what I'll pretend, this is a service provider. This is a service provider. And this is a private company. There we go. So we'll say this, just for the sake of it, it doesn't really matter. This is an AS number 65001. This will have an AS as number 10. I have absolutely no interest in these numbers. And this one, an AS number 208. Obviously, I've made them up. All right. Now, the point is, this private company here will have all of its devices in there, of course, all in here, and they will run an IGP. The IGP might be OSPF. To a point, it doesn't matter. What does matter is that I managed to spell that O correctly. It will run OSPF, which you hopefully will remember is an IGP, an interior gateway protocol. This one, number 10, the service provider, will run an IGP, and we'll say that this is running ISIS. Again, just for the sake of argument, fantastic. Then finally, we'll have this one down here. This one we'll say is running an IGP, it most certainly is, and we'll say it's running RIP. Pretty unlikely, but one never knows. So there we go. All right. So what we need is the ability for these devices to communicate. There is a lot of information. We are using the internet to help us speak together. Consequently, we will have another protocol running here, and this is where BGP will sit. This is an EGP, an exterior gateway protocol. It is an exterior gateway protocol because it's running on this link here, which is external to both AS208 and AS65001. It will run on this link here, and it will run on this link here. Fine. So BGP runs external to the ASs. It connects, BGP connects ASs. Fine. Connects AS, autonomous systems networks, we'll say. Fine. Now, a good question is, or a good statement is, well, hang on, if this one here is running OSPF, surely OSPF is not exactly compatible with ISIS, is not exactly compatible with RIP, is not exactly compatible with OSPF. Yeah, you're right. So what happens to make this work? Updates from here, device A will hit device B, we'll say, and that information will be redistributed. Put in, yeah, that'll be redistributed. I'm trying my hardest to make this neat. Redistributed into BGP. Then the data, if I pick up my green, will come along here, and it will come here. This device, ABCD, this device will say, just hang on a minute, I want to check that you are allowed in. If it is, that point is relevant. I'm going to come back to that on the next slide in about probably a couple of minutes. D will say, hang on a minute, I want to see if you are allowed to come into here. So it does a check and it says, oh, yes, you are. So it will redistribute it into ISIS or into BGP, actually, because we're running BGP as well. The data will move across here, and sooner or later, it will get to device F here, and out it comes to be redistributed into here, to zoom along here, where again, device G will say, hang on a minute, I want to make sure you can come in here. And it does. It will be redistributed into this system, moves along through here. That's G, that's H, that's I. And sooner or later, of course, it will go out of here and it can go on its way here. Arriving at this one, and device C will say, hang on a minute, I want to make sure you can come in here. And if you can, in you go. Fine. And this is how the system works. Okay. So the takeaway, or the thing I want you to realize here, is that there are these AS numbers, and these are the ratings for them. BGP runs between ASs, and the AS will have some kind of an IGP. They might also have BGP running internally. Yeah, they might not, but they might. So I'll just put BGP as well. So they've got OSPF and they might have BGP. This one has ISIS and they might have BGP, and it will be called internal BGP. Fine, and the same applies down here, RIP, and they might be running BGP. Okay, so that's what I wanted from that slide. Okay, building on from that is this. If I'll just duplicate that slide. So if you just bear with me a second while I do that. All right, there we go. So that's it, should be duplicated now. Good. So what I want to do now is just get rid of this AS number business and talk about, this looks as though I'm going off on a tangent. I'm not. Yeah, you'll see what I mean. Let me just get rid of these little lines here. IGP, I'll leave that there. I'll leave that. There we go. There we go. And get rid of that one. Get rid of that one. Get rid of that. And life is good, or it will be in a minute. BGP. Right. There we go. Good. Done. So now, this is where it looks as though I'm going for a tangent. I'm not. If you cast your mind back to your previous LINX courses, we have a situation here. This is a switch. This is a switch. This is a switch. This is a switch. Fine. On this switch, we have a server. There it is. Quite a wonky server, but there we go. Alice in Wonderland in height. 2 servers. It might be DHCP. It really doesn't matter. It might be DNS. It might be a data server. I don't know. But you have your clients upstairs here. Now, the fact of the matter is, these switches will be connected. So your clients, your users, if it's a DHCP server, they can get an IP address from here, no problem. You say to yourself one day, I tell you what, if that cable here breaks, we have got a major problem. We can't get to our servers. I tell you what, I'll put another cable in. So you do. Fantastic. When you do that, you run a risk that you might get a layer 2 loop. Yeah, because a DHCP DHCP request is a broadcast. What could happen is, I'll put a broadcast. What could happen is this. The data will leave here. The request will leave here. It will go to this device, it will go to this device, it will go to this device, it will come out of here, and it will come out of here. And it will make its way out of here as well. But what could happen is that this data here could go back out there, and this one could go back out there. These would then be propagated all the way over here, and this is disastrous. This is a broadcast storm. It kills your network. So what you do is, to stop that happening, you would implement something called spanning tree. Spanning tree will block an interface and it blocks potential loops. So spanning tree blocks those loops. Fantastic. Now you might be saying, what's that got to do with BGP? Absolutely nothing. But STP stops layer 2 loops. So we move on a bit further in our quest for perfection in our routed networks. And we have this. Just get rid of that. We could have these. We could have a system here in Los Angeles, good for us. We could have this in San Francisco, and we could have this in, we'll say, Leeds. Fine. You connect them like this, life is good. And again, you have it, we'll say, a giggling here, I don't know, a giggling here, and life is pretty reasonable. Your updates flow, data flows between LA and Leeds, and life is pretty good. And again, you say to yourself one day, if these links between LA and San Francisco break, or the San Francisco Leeds breaks, we're in trouble. I tell you what, I'll put in a backup link here as well, all right? A 10 meg link. Then you set it up, but unfortunately, you use static routing, yeah? Unfortunately, you do it wrong. So what happens now is data would egress here, and might egress here. So now you've got a layer 3 loop, and this is not entirely wonderful, you know? So there is a mechanism in place to stop layer 3 loops, and that is TTL. Yeah, in the IP header, there is a field called TTL, time to live. It will decrement by 1 at every router hop. And when it gets to 0, the data is dropped. Data dropped. So, and whoever's dropped the data would then inform the sender. So the point is, the TTL stops layer 3 loops. Spanning tree drops layer 2 loops. TTL stops layer 3 loops. But now is the start of the BGP stuff, because what we've got here is a potential loop. Yeah, data could egress this device, and it could come all the way around here. It could loop, which is not terribly wonderful. Again, it might be what you want, it might not. But so what? The so what is this? This is the first an introduction or an introductory part to BGP attributes. All right. If I was to say to you, I can't spell attributes. BGP attributes. There are quite a few of these. All right. The one I'm interested in as we speak is this one called an AS, as in autonomous system path. All right. This is an attribute. It is one of a list of attributes. You will see it as the course as the meeting progresses. All right. Here is the AS path. It is a big fat empty. There is nothing in it. All right. Yet. So I am talking about AS65001. All right. We'll say device A generates some information. It will transit to device B, and it will probably transit to device C as well. But really, I'm interested in getting to device B. Device B will look at this data and it will say, aha, I will redistribute you into BGP, and as you leave my system here, I will put RAS path, RAS number in this path. So it puts 65001 there, and it will put a space in front of it, so to speak. The data will come across here. It will arrive at device D. Device D will say, hang on a minute, I want to make sure you are allowed in here. What it's actually doing when it says that, it is looking for the presence of 10 in this AS path. All right. It sees that 10 is not in this path. Consequently, the data is allowed in. And it will zoom across here, does whatever it has to do, and it will egress F. As it egresses F, device F will put 10 in the AS path, and it will prefix it with a space. The data comes along its way here, the update comes along its way here, it gets to device G, and G will say, hang on a minute, I need to make sure you can come in here. And what it's doing, it's looking for the presence of 208 in the AS path. Well, of course, it isn't there. So the data is allowed in, moves across here eventually, and egresses device I. As it egresses device I, that edge router will put 208 in the AS path. Fine. Data will move along here. It will eventually arrive at device C. Device C will say, hang on a minute, I want to make sure you're allowed in here. So it's looking for device, it's looking for a number 65001. Well, of course, there it is. This device then, listen to this. This device will then say, by default, there's that words, by default, you are not allowed in here because we have a loop. We sent this out, you are not coming in. The data will be dropped. So that is an introduction, if you like, to an attribute called AS path. It will stop, it will stop loops. All right, AS loops, if you like. That's what it does. So the AS path by default will stop by default. AS path attribute, better put that, attribute, I'll put can stop loops, which is all well and good. In fact, it's fantastic. What you really, really, really want to realize is that within this AS path, if I just get rid of that, get rid of that, get rid of that, there is some really good information, because here is the originating AS. Here and here are ASs that the updates have passed through on their way back to your system. And this one here is the closest one to your system. So, which is quite useful, all right? And it can be used for other things as well. So that is the first thing about the attributes, all right? So there we go. Now, consider this. AS path attribute can stop loops. By default, it will. What if you have this system then? So here it is. We've got an edge device here. There we go. And this is, we'll have another router in here. We'll say AS number 7. It really doesn't matter. There's a router. There's another router. There's another router. This is AS 211 or 208. Why not? And over here, we have another router, like so. And this is AS7. Fine. Here's the thing. If I just put routers in here, again, this is quite relevant what I'm going to do now. This device here, this one on the edge here, belongs to AS7. This device belongs to AS7. This device belongs to 208. This device belongs to AS208, and so does this one. Fine. This one belongs to AS7, and this one belongs to AS7. Fantastic. For your information, you need to realize that when these numbers are equal, these are running internal BGP. There's two types of BGP. There's just the same protocol, but there's internal BGP. Consequently, because 7 is exactly the same as 7 here, these are also running internal BGP. And guess what? 208 is the same as 208. 208 is the same as 208. So these are running internal BGP. Fine. Then, because 7 and 208, sorry, are not the same, this constitutes external BGP. Because 208 and 7 are not the same, that again constitutes external BGP. Fine. That redistribution I was talking about can take place here. But the fact of the matter is that, again, my AS path attribute, there's the AS path attribute. There is a big fat empty. But as the data egresses here, it will put a 7 in here with the space. This will be checked for a loop. There isn't one. It will enter, it will egress 208. 208 is put in here. Well, of course, as the data gets to this device here, we'll say device A will look into the AS path attribute and say, hang on, let me just tighten that up a bit. Yeah, this device here will say, let me just check if you're allowed in. Ooh, 7, word number 7, oh, it's looping. But this behavior can be changed. And this is a thing of BGP. There are different commands. One is allow AS in. So the default nature of BGP can be overridden by a few commands. Yeah. So allow AS in will now allow that in, and life continues. So the point I'm making is, by default, the AS path will stop it. Yeah, will stop the loop, whereas it can be overridden. Fantastic. So there we go. So there is internal BGP and there is external BGP. Okay, fine. The last thing I just want to talk about on this is this kind of thing. Yeah, if I go into here, I'm still talking about IGPs, well, ish, and in particular, I'm just talking about RIP now. RIP has a router here. It has a router here, and it has a router here, and finally it will have a router here. This is the destination. I'll put another one down here. There is E, the source is here. Right, the source. The fact of the matter is that to get from A to D, device A could go via A, B, C, and D. That metric, because this is what we was talking about a few minutes ago, is a hop count. So data would leave here, it would hop over that one, it would hop over that one, and it would hop over that one. So the metric for this one is 3. Fine. And it could go this way And the metric for that, there are 2 hops. So it could go AED. AED. Fantastic. And the metric there is 2. RIP will use the path of least resistance. It will use this metric. Good for it. The point to this, again, if anyone's thinking, I thought this was about BGP, the guy hasn't hardly mentioned it yet. Well, I have, and I will. But the point is, RIP will send data this way. There's nothing you can do about it. This could be a 10 gig link. That could be a 10 gig link. That could be a 10 gig link. This could be a 10 meg link. This could be 10 meg. Well, I mean, come on. The top link, the top circuits are much more preferable than the bottom. But I'm afraid that's a shame. Your RIP is adamant it's going to go this way. All right? Which is unlucky. Same time, OSPF will do this. It might have exactly the same topology. Why not? Live dangerously. And again, this is A, this is B, this is C, this is D, this is still E. Well, OSPF, if I wanted to be a bit dramatic about this, but I don't really, we could say OSPF uses Dijkstra's algorithm. Dijkstra's algorithm, and it will calculate whoops, I spelled it wrong. Dijkstra's algorithm, and it will calculate a cost for each of these links. And it's based on something called a reference formula, a reference value, reference bandwidth actually, divided by the actual bandwidth. Actual bandwidth. So what I'm just going to do is cheat. This is 10 to the 8th. The actual reference bandwidth is 10 to the 8th. So there's that. There's the, to the 2, to the 3, to the 4, to the 5, to the 6, to the 7, to the 8th. Fine, 10 meg, 100 meg, 100 meg. All right. So if we was to say that this is, let's say this is 10 meg. All right. This is 10 meg. This is 10 meg. This is 100 meg. Oops, the daisy. Sorry. There we go. Try again. This is, what did I say, 100 meg. So you can believe here then, chaps, if this reference bandwidth is 100 meg, and this link here is 10 meg, so that's going to be 10 meg divided into there, is going to be 10. So the cost of the top links, plural, is going to be 10, is going to be 10, is going to be 10. Cumulative bandwidth for that one, cumulative metric, I should say, is 30. Here, 100 meg divided by into 100 would give us a cost of 1, give us a cost of 1, and the cumulative cost for that one would be 2. So unsurprisingly, OSPF would choose this one. Now, all right, OSPF, you can change the value of the cost. No problem at all. But that's your lot. All right. OSPF will still put the lowest metric into its routing table. RIP will put its lowest metric into its routing table. And that's it. So, fine. Then we have this thing, BGP. So now we can have this type of a system. And there we go. That will do like that. There we go. Hey. I'll just do 2 more and that'll do. Oops, that's not right. Sorry. There we go. Right then. RIP, the one I was just talking about there, is a distance vector protocol. Yeah, it counts the number of hops. So we have this thing here now. is BGP. Fine. This is AS7, we'll say. This is AS21. This is AS346. These are of no interest to me whatsoever, these AS numbers, but they do have to have an AS711, we'll say. Fine. There we go. Fine. This will belong to AS7, that will belong to 21, of course, that will belong to 21, that will belong to 346, 711, etc. Now, what will happen here? What can happen here? BGP will look at this system and it will say, aha, here's my destination. Fine. BGP will say, right, I can go this way. I can originate from number 7. I can then transit number 21. I can transit 346. And sooner or later, I will get to 711. That looks pretty reasonable to me. Or I can leave number 7 and I could get to number 711 this way. So now, the interesting thing here is, if this was RIP, which is RIP is a distance vector protocol, counts its hops, data would leave here, that would be 1 hop, that would be 2 hops, that would be 3 hops. Fine. And of course, this other one would be just coming down here, 1 hop. So it's a distance vector, which would come back with the metric. BGP is a path vector protocol, a path vector. So in just the same way that RIP had its metric of 3 and it had its metric of 1, RIP would pick this because it is the path of least resistance, it is fewest hops. BGP does exactly the same. Yeah. So BGP would now, I'm using a bit of poetic license here, to be honest, but BGP would look at these and say, aha, I can use this top path here, which means me, in effect, hopping through 3 systems, or here, I can use this one. So this is a shorter route. I will choose this route. Fantastic. So what will happen now, and this is really, 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 really quite important, that is the best path. That, or the best route, that will go into its BGP table. Okay? Again, good for it. I did say the AS path can be used for all sorts of things. And yes, it can. It can be used to stop loops, and it can be used to influence the path chosen. All right. How does it do that? Well, BGP has a system called AS path prepending. All right, which we'll see a bit later on. There is a mechanism called AS path prepending. And what it can do, because you might prepending, there we go, you might not want data from here to come this way. Yeah, so there it is. You don't want that to happen. But if this was RIP, if this was OSPF, RIP, whatever, you have no choice, you know. But you can use prepending, and what will happen here is, as you speak to this neighboring device here, yeah, you can tell it to put the AS path in, we'll say 5 times. I've made it up. So there's 2, there's 3, there's 4, there's 5. So now what BGP will do, it will say, right, I can get to this destination down here. I could go egress 7, I could transit 21, I could transit 346, or I could do 711. That is, we'll say, 3 hops. Whereas if I choose this path here, there's 1, 2, 3, 4, 5 hops. So, of course, the first one is where it's egressing from. So there are fewer hops for this one. So this one now will go into the BGP table. This, in effect, would be the best path. Yeah. So the point is, because it's an attribute, we can use it to affect the behavior. And I just pick on AS path prepended because it's quite simple to see what happens, you know? And while I'm just talking of that for a moment, I could throw something else at you. Because in this list, you sooner or later, you will see a list of attributes. And another one, just to give you food for thought for a moment or two, is one called the weight. Now, all right, it's the Cisco proprietary. But what it is, it does this, proprietary. This is the last one I'm going to mention. We could have our system here. And again, we'll have this one like this, fair enough. I'll stick with AS7 for no particular reason. I'll stick with that. It might be we'll say simplistically, we're talking to a service provider here. I'm not talking to another system anyway. That's 211, 211, 211. We'll do this. All right, fine. We will say that this is a 1 gig link. Fine. And we'll say that this is a 10 gig link. Fantastic. Well, what we can do, we can choose or we can influence which interface data and egress. Is it going to be that one? Is it going to be that one? And all we have to do is apply this thing called a weight. Again, we are talking to our neighbors. We'll have an IP address on here, of course. We'll have an IP address on here. We'll have an IP address on here, and we'll have an IP address on here. We'll just say, for the sake of argument, this is 200.1.1.0/30, and this is 200.1.1.4/30. So here will be .5, we'll say. There would be .6. There would be .1, and there would be .2. Fine. So all we have to do under our BGP process, which we kick off similar to this syntax here, we'd have router BGP number 7, as in the AS number. We would then have, look at this, we would then have a neighbor, number 200.1.1.2. There you go. And it's in remote AS number 211. Now look here. What this means, of course, is that 7 is not the same as 211. So consequently, that is going to be running an external BGP, which I'll just write at the back of it. So that's running external BGP. And what we could then do, if we wanted, we could put neighbor, we'll set up the other one just for the sake of argument. Neighbor what we'll do, chaps, in case anybody's getting desperately thirsty or anything like that, we'll have a cup of tea about 11ish. In remote AS 211. Let's get this to. So we've got the two neighbors set up. Then, if we really wanted the data to go out of, we'll say .5, we can put neighbor 201.6 there. We can apply a weight, right? The weight, the default weight, it has a default weight, right? We'll say it's 100. If I make this bigger, in other words, 200, I could have made it 101. It makes a difference, really. Actually, that's a lie. It makes a big difference because it's going to affect the behavior of the system. Because now, as if I just write in black, the weight on this interface here is 100. The weight on this one is 200. So what's going to happen now? Data updates will, by preference, come this way. Fine. Yeah. And then, of course, if you wanted to, you could make that 201 the weight. Consequently, now the data would go out there. Yeah. So this is the whole point. Yeah. BGP can be influenced, and the weight, AS path, are ways of doing it. All right. So I just wanted to throw that at you, all right, to set the scenario, as it were. Okay. So there we go. So now, as I've been speaking there for almost an hour already, goodness me, how time goes when you're enjoying yourself, right? So now you should realize RIP, OSPF, EIGRP, ISIS, they are IGPs. They will calculate the best route. They will put it into the router table. Fantastico. BGP is an external is an external routing protocol, runs between ASs. The ASs are identified by a 16-bit number, and BGP, its behavior can be influenced. Yeah, there are two tremendously useful attributes that we just covered there, the weight and the AS path. All right, fantastic. So with that in mind, I'm just going to drop that out of the way, he says, and there we have it. So now, hopefully, you will be back on my routing protocols. I'll just make sure by sharing that again. Let's have a look. Nope, that's not right. I get dead paranoid about getting the wrong slides up. So just bear with us. So I'll do a new share on here, and there we have it. So now, with a bit of luck, you'll be able to see the routing protocol slide. Is that right, Holly? Are you still here, Holly?
Yeah, no, that's right.
Smashing. So with that in mind, we'll move on to the next slide. He says, we'll move on to the next slide. Sorry, I can't do it. Now there it is. It just reiterates what I'm saying. Yeah. What is BGP? It is Border Gateway Protocol. We run version 4 of Border Gateway Protocol. Yep, it's an EGP. Contrasting IGPs and EGPs, they both build routing tables. Absolutely. BGP has its own table, which is absolutely tremendous. Yeah, puts all routes for destination in it. So consequently, should something happen to the chosen route, the best route, others are available straight away. Yeah. IGPs are run within an AS, whereas EGPs run between ASs. Absolutely. Big deal, big deal. The concern, IGPs converge really quickly. And when I say really quickly, I mean compared to BGP. But in truth, ISIS converges depending on number of devices, but it's really fast. An OSPF, maybe less than a second or a second-ish. RIP takes a bit longer, but nobody would use RIP anyway. Whereas BGP, there is such an amount of data. BGP tables can take a while to be built. Yeah, it is not a light undertaking to clear your BGP tables, because it can take a good while to minutes, to reconverge. Rather, BGP is built for reliability, scalability, and it carries the entire internet routes. Apparently, it's about going on for 1 million routes, but that figure changes consistently. So anyhow, there's a bit of a comparison between those BGPs, between IGPs and EGPs. Now then, it is 11 o'clock. So I'm about to have a break for 10 minutes and have a cup of tea, and then we'll come back and talk about the routing aspects of BGP. Right. So here we go. BGP, all right, Border Gateway Protocol routing tables. The fact is that BGP builds its own table, yeah, the BGP table. And it does this by accumulating data, all right? The fact is it has what they call a RIB, a routing information base. And I suppose if I was just to drop back into PowerPoint for a minute, I could just illustrate what it is I mean by that. So just bear with me. So there's that, and I will just share that screen again. So hopefully you can see back into my Picasso-esque drawings. Yeah, okay. And it's this. So I've got, there's one slide. Here is a router. Oops. Here is a, well, here is a router. Why is my ink not running? Yeah, so here is a router. The fact of the matter is, it's a 3D router this time. We could have our networks hanging off a router. Yep, so we could have a switch running out here, fantastic, with 172.16 something or other. We could have another network here. So we'll specify our networks here. The fact is that BGP, Border Gateway Protocol, has this thing called a RIB. It is a routing information database. It is not exclusive to BGP, routing info base, routing information base, or database. Fine. And what this is, there's RIB. This comprises of, there's three sections basically. There are three sections to it. One is where is info from peers, from BGP peers. Okay. So in other words, there has been a router up here that has sent its information in, that in Los Angeles will say, there is another one over here from San Francisco. It will send its information into here, and multitudinous others will do the same. Fine. Here, there are the local networks. These are local to this device here. So in effect, they are broadcast domains on there. Now then, an interesting thing here is this. If we have a network here, we'll say 172.16, 10.0/24. It really doesn't matter. 192.168, 20.0/24. Again, it doesn't matter. But the fact is that they are local to that router. If we go back to this type of system where I have a router there, where I have an internal router, we'll say this is AS7 again, AS7, and this is in AS7, well, consequently, of course, I don't need to put the AS there really, so I'll take it out. We get very pedantic about these things. There we go. And we'll have AS7 up here. Now, really, something you need to be aware of, and this will soon be visible in actual BGP system. If I do have 192.168, 20.0, we'll say just 20.0/24 on here. Fine. This system here, this one, will generate information for number 7. And take my word for it, this attribute that we've already mentioned, the weight, it will be set to this, 32768. Fine. That is the default value of the weight when an update is spawned, yeah, and it stays within, or it's still within the AS, yeah. So if you see a weight of 32768, you know it is a local network. All right. You'll see that. I just mentioned that because you will see it pretty imminently. All right. So anyhow, that's as a side note. So we have our routing information that's got 3 sections. One is information coming in from BGP peers, i.e., e.g., Los Angeles and San Francisco. Fine. Then there is that from the local networks, local information. Fine. And then the third section is processed information that is ready to go out. Yeah. Processed info ready to go out. Ready to go out of the device to go out to peers. Okay. Fine. So that's really all I want to say about that. But that is the routing information base. Yeah. So then all of that information will comprise the routing table, as it were, the BGP table, and then you will get the best route selected. Just move my coffee. So there we go. So I'm going to drop that down a little bit and go back into my slides. Right, fine. Sorry, just distracted there. So now I am sharing the BGP routing tables. Okay. So what we've got here then, we have a device, we'll say here. Yeah. Here comes the information in from our BGP peers. Yeah. So it's going to come into there. Then it will hit the BGP process, the route to BGP space 7, the process number. This information will hit the in process. It will hit the filters. It will go through our processing system. If we want to allow the data in, if we are allowing it in, we will accept it. If not, we will discard it. Fine. So this information will go into the BGP table. Fine. There is also the information from the local database, etc. Out of those multiple routes in the BGP table, the best routes will hit the routing table. Okay. The best routes are, of course, dependent upon the attributes. Okay. So there we go. Then there is the BGP out process, which is exactly what I was saying, and the best routes are passed to our BGP peers. So this is the RIB, the routing information base being built. Okay. Here's an interesting thing. Right. You can see here, actually, in the BGP uses different types of messages. All right. They are exchanged between BGP peers, BGP speakers, BGP devices. Fine. And they are all, those messages are open here, update, notifications, keep alives, and there is also a refresh. All right. So within there, what is well, I was going to say extremely important, but what is really interesting is there is a message type, there is a header. All right. The header is 32, 64, 96, 128 bits, right? 128 divided by 8 is 16. So there are 16 octets here in the header, and they are all set to 1. Whoopee-doo. Why? Because that is for consistency and for legacy, if you like. Then it gets slightly more interesting here, because you've got a length, 16 bits, 2 bytes, 2 octets, and a type, again, 8 bits, 1 octet, right? So this gives you a system here. There are 4 bytes, 4 octets, 8 octets, 12 octets, 16 octets, 18 octets, 19 octets. That is the minimum size of the open message, all right? it's interesting because in this type, here you go, 1 means the message is an open, right? That's what it is. It's related to opening up. Number 2 is an update. The message is an update. Now, this is a big deal because the update brings, funnily enough, updates to diff peers, and it will include routes that have been withdrawn from service for whatever reason, and they will also include routes that have been added to the service. Yeah, they will include routes that you have changed. BGP uses a lot of, in effect, it's policy driven. Yeah, if you say your policy is to have an edge device have 2 connections to every other device it talks to, you will use gig 0, you will use gig 1. We want gig 0 to be our primary connection. So that would be a policy, yeah? Just for example. Equally, what's also important in here, in the open, yeah, we've got these, the minimum size of, I might have already said it, I can't remember. The minimum size of an open message is 19 octets. And there they are, 4, 8, 12, 16, 17, 18, 19. The maximum size is 4096. Again, whoopee-doo. There's a big difference between 19 and 4096. What comprises that difference? Well, the devices, they are negotiating. Yeah, they are talking to each other and they are saying, can you support this? Can you support that? Yeah, just for example, there is a system called route refresh here. Yeah, in days gone by, well, in days gone by, what you have to do when you change your policy, when you change your weight on an interface, when you change your AS path prepending on a system, you have to force an update so that your peers know about it, right? In days gone by, this could take a long time because BGP sits on top of TCP. It runs on TCP port 179. Fine. And if you really forced a reset, it could take ages to rebuild, you know? So Cisco have developed this thing called a route refresh, where you decide to turn it on and the devices will say, do you use to each other, do you support route refresh? Yes, I do. Do you? Yes, I do. You know, and they know that's what they do. So in these, not only does these open messages get the ball rolling, they also negotiate just what the peer devices can do, which I think is pretty clever. But there you go. So that's the open message type. It's important. Just so you know, the notification is reporting on errors, and the keep alive, BGP has a keep alive default value, or a default hold value of 180 seconds, right? What the system will do, the BGP devices, they will see that the hold timer is set to 180. By default, that is divided by 3, which of course gives you 60, and that is your keep alive value. Fine. So they don't actually set one, they just divide the hold timer by 3. Yeah. And if for any reason the two don't match between peering devices, they will choose the lower value. But so there you go. So the fact is that really opens a session. The TCP session is already set up, and then the BGP will cut in, and it builds a session between the peer speakers, and they negotiate what they can do. Fantastic. Notification is reported on errors, and the keep alive is just that. Notice I haven't mentioned the updates, really, because the updates are here. The updates, like I say, is a big deal, dudes. It uses the same header, right? In the message type, it uses the same header. I just want to jump back a slide. As they open, sitting on top of TCP, you then have the standard BGP information, whereby the devices will say, I am running version 4. This is my AS number. This is my router ID, my BGP ID. Yeah, so that is that. Yeah, the standard header. In the BGP update packet, this again is a big deal. It still uses the same header as the open packet. It still has those 19 fields, 19 octets, and then it has information below it, which is what this is trying to illustrate here, right? In the update, like I said, it will say how many routes are being withdrawn, yeah? Or this is the length of the withdrawn routes. Then it will itemize the withdrawn routes. Fantastic. The update packet might not include any withdrawn routes. Fantastic. But it will have routes that have been added. Yeah. So, or it might not have any that have been added and only have withdrawn routes, you know? So that's what these first fields here are related to. Yeah. What are your withdrawn routes? How many are there? What is the length of the information of the path attributes? Of course, this is helpful because once the system knows the length, it will know where this header comes. This is the network layer reachable information. This is routes that have been added to the process. Yeah. If you only had 2 routes previously, another 10 have been added. Fantastic. You know, and that's what this is. Look, yeah, there is a TLV, a type, a length, a value, and within that there are the codes of just what has been added. Yeah, this is really quite a big deal, this update packet. You know, it's not something you can sort of gloss over. Good grief, it's 11:30. I hadn't realised. So there are the open and the update packets. Fantastic. Yeah. And here, look, are the prefixes of the routes added. Great. And there it is. Now look, this again is a big deal because we've got the update packet, we've got our path attributes. What are they? Well, a TLV, it is a type length value. Within the type are flags that indicate the type of attribute. And what are they? Well, here they are. There is a well-known mandatory, there is a well-known discretionary, there is an optional transitive and an optional non-transitive. What does that mean? Well, this well-known mandatory, that is saying that, look, there are some attributes that have to be included. They must be included in BGP updates. These will include such things as the origin, where the information has come from, which could be from the network statement under the routing process, or it could have come in from the redistribution process that I mentioned as well. Fine. So that is the origin. There is the AS path. You can appreciate, like I showed you, if we're using the AS path attribute to influence what's going on with our traffic, it has got to be included in the updates. Absolutely got to be. Yeah. And so there's then the next hop. Yeah. Well, of course, it goes without saying, but I'm going to say it anyway. If my system, if my local interfaces will say, I don't know, 200.1.1.1/30, well, my next hop really has got to be 200.1.1.2/30. If you ain't got that information in your BGP update, it ain't going to work, you know? So there are well-known mandatories, yeah? They have to be included. There are well-known discretionary. Yeah, they could be included in updates. They might not. Yeah, you'll see a list of them imminently. Then, apart from well-known, there are optional. Yeah, there are optional types. There are optional attribute features, if you like. They could be transitive. They will be passed on by neighboring devices, neighboring systems, or they might be non-transitive. They will only go to a neighboring device. They will not be passed on. Yeah. So just realize that there are these. Okay. Then to illustrate that is this. There, as you can see, are your well-known mandatories. There is the origin. Like I say, that is where the information has come from. It could be generated by a local network statement, or it might have been redistributed by a device down the line. The AS path, what can I say? It is used to keep track of where the information has come from. So where it's originated from. So it's got to be the mandatory. Good heavens. Yeah. And the next hop, how it's going to get there. Of course, there is an optional non-transit. This MED, this multi-exit discriminator. I just said that on the previous slide, there was optional non-transitive. It will go to a neighboring system and it will not be passed on. What does that mean? I'm afraid it's back to God, I forgot what it is. Afraid it's back to PowerPoint for a minute, chaps. Just bear with me. If I go back into here, because this is again quite important. Here we go. Right. So now I should be back in my blank PowerPoint. Oops. Sorry, pressed on the wrong button there. And it will give us, hello, there. What's going wrong here? Right, just a minute, chaps. Right. With a bit of luck, can you see my scribbles, Holly?
Yes, we can. We can see the PowerPoint that you've been writing on.
Perfect. Thank you. Right. So now, this is an example of that optional non-transitive, and it is a multi-exit discriminator, also known as the metric. Also known as the metric, absolutely right, and it is the multi-exit discriminator. And it's this. Now, if this is our system, right? There we go. There's our system yet again. Fantastic. All good stuff. As you can see, we've got more devices this time. Now, we could have this type of a situation. We could have this if I wanted. There is nothing to stop me having an edge router here to my service provider here. And we could have a connection here. And we could have a connection here. And we really want return traffic to come here. So we can request, using our multi-exit discriminator, we can request influence that return traffic comes there by configuring the MED. Yeah, the MED, the lower the value, the better. So we could, the default is 0, by the way. So we could leave this one as 0, and we could just make this one 10. That is the value we are assigning courtesy of the MED. That will go to here, and so will that go to here. And the service provider will automatically send return traffic along this link. Yeah, so we can do that. We could also do this. We could now have this type of system, and we could have a service provider here, like so. oops, daisy, got a bit excited there. And if I just do this now, so now we could have a connection to that one, and we could have a connection to that. And it might be that we would prefer, this is external BGP, of course, and be running here. There we go, ABC. So we could say we want that one. So now, of course, we could use our multi-exit discriminator here, and this would be the favored route. Yeah. So where does the non-transit come from? Well, of course, the MED, these values are sent here, and that's it. They don't go any further. That's it. Whereas the AS path, this is number 7, the AS path, oh, good heavens. The AS path attribute there, as it leaves here, would have number 7 there. Well, of course, it needs to be passed on, and of course, updated with 7 and 211. So this is a transitive, in point of fact, this is one of those well-known mandatories, of course, but it is transitive, it will come all the way through, whereas the MED is non-transitive. It will be stripped off. It's stripped off the updates there. Okay, so there you go. Fine. So now, as I come back into here, new share, and if I jump back into there, and bit of luck, we should now be back on the BGP attributes. Yep, is that right, Holly?
Yeah, that's right.
Perfect, brilliant. And here you can see a bit about the attributes here. Yeah, there is the origin. Like I say, it's where it has come from. Was it put in with the network command? Has it been redistributed? Whatever. The AS path, what can I say? The next hop is, of course, the next hop to the next device to get the ball rolling. Fine. Then there is the multi-exit discriminator, optional, non-transitive. And then suddenly there's a couple of new ones here. The local preference. The local preference is used a lot. It is an AS-wide system. You'll come across it very shortly. Then there are these, the aggregator and the aggregate, the atomic aggregate. This is to do with summarization. Yeah, summarization, of course, conserves memory and the like. Yeah, and this is the device that has done the aggregating, summarizing, if you like, and the end result. Fine. There are these communities. These are a tremendously big deal. Yeah, these are used to influence. They are used to influence behavior, treatment of information. They are used between service providers and customers and service providers, and between different peer systems. They are a very, very important part of BGP. Yeah, unfortunately, they are so important, there is no way we could even scratch the surface in such a short period of time. But the point is, though, they are transitive. They are optional. You don't have to use communities, but you can. You could, for example, use a community to request that a peer device does not forward certain information. They don't export it, basically. They can take it in, they can use it on their internal BGP systems and do whatever they want, but they are not allowed to forward it. Yeah, but it's transitive. Yeah, so that could be forwarded on and forwarded on. Fine. Then there's the originator identifier, yeah, which will of course identify the point, the point of origin. And finally, at least on this slide, there is a cluster list. There are things called route reflectors. It's a big thing is a big thing in BGP. A BGP device, an internal BGP device, if it receives an update from an external BGP device, it is not allowed to forward it. That is one of the rules of BGP, yeah, which can be traumatic. You could lose some information. So the way around this is to use a fully meshed network that will do the job, or you can use these things called route reflectors. If you get a number of route reflectors in, you will eventually put them into what they call clusters. Yeah, even as few, I suppose, as 4. You could have 2 clusters of 2 each, or of course, if you have 6 or 8, you could have bigger clusters. You know, but again, it's one of those things that we can't get into. So anyhow, just relax and think there are various attributes. Those are the big boys, especially the AS path. It is a list of AS numbers, the information the update has traversed, absolutely. The first one in the left on the right-hand side is the point of origin, and then, of course, subsequent ASs that the information has traversed. And like I said, the next hop is obviously an IP address to get to it. Interestingly, I mentioned the weight for a locally generated network, all right? Or an update for a local network. The weight was 32768. It is still in the AS. Consequently, as far as everything is concerned, there is no next hop. The next hop is for when it goes out. Yeah. So you would find whenever you've got 32768 as the weight, the next hop will be 0.0.0.0. Yeah. So there's nothing there. And then finally, on this slide, at least, the origin, as I've said, defines where the information has come from. Is it from an IGP? Are you running OSPF? Have you set a network statement in there? Are you running your BGP with a network statement? You know, or this one is not used very much actually. And the incomplete means that data has been redistributed. You'll see what I mean when I get onto my topology. All right. The EGP is not terribly used, if at all, you know, whereas incomplete is, and so is the IGP. And in point of fact, the origin is an attribute that helps in defining the best path. Yeah. So actually, this IGP here and the incomplete will be back in a few minutes to bite us. Okay. There's my loop prevention. We've already covered this. We have information here being generated somewhere AS1. Yeah, I could tell, how do I know it's generated from AS1? Well, it's the first one in the list. Yeah, I'm just going to have to drink a coffee. Bear with me a second. Right, so data egress is AS1, puts AS1 in here. Goes up to AS2, traverses AS2, egress is out here, AS2 is put in the list. You can use a comma, use it as a space, but there you go. Ingress is into AS3, egress is AS3, AS3 is added to the list, and then of course it's AS4, out it comes. The edge device here on AS1 will say, oh, not sure about this, we generated this, look, and it will block it. But that can be overridden. Fantastic. Here we have it. So now, like I've said, OSPF, RIP, etc., they will pick the best route, the lowest metric. But BGP can use different selection criteria. Okay? And there they are. At last, you all say, good heavens, there is a list. They are processed in that order. The BGP process will, in your system, it will look at a route. It will look at a router. If a router, like it says here, if a router has 2 interfaces or 3 or 4 live interfaces, yeah, it will look for a highest weight. Now, the point to this is it is local to a router. Yeah, it is nothing to do with anybody else. Yeah, it's Cisco proprietary. So if my edge router has a connection 200.1.1.1 going to 200.1.1.2, and it's got another one 201.1.5 to 201.1.6, and I really want to use that 200.1.1.5, I will assign a higher weight to it. Yeah, fantastic. Now, I could show you that. Just bear with me a minute. The point is, it is local to a router. Okay, so what I'm going to do is hopefully this. Actually, I'll just finish going through these as they were here. If the system finds that on a router with two interfaces, the weight is not set on either interface, consequently, the weight is the same because it assumes the default value. BGP will then say, aha, there are two interfaces here. They are both the same weight. I tell you what, I'll have a look, see what this thing called the local preference is. And the local preference is local to an AS as opposed to a router. What that means is this local to a router applies to a single router on a network, whereas here we might have two edge devices or 3 or 4 edge devices, and we could use a local preference to select the one we want to communicate out of. That's what the local preference is. And look, I said the origin was going to be back. Here it is. Its selection criteria now, if the weights are the same, if the local preferences are the same, it will choose the route originated by a local router, which you might remember is, if I just jump back a bit, there's the IGP, yeah? That is locally generated, yeah? Fine, so it would do that. Well, of course, if the weights are the same, the local preference is the same, all of the updates are generated by a local router, it will have a look at the next one, and it will be looking for the shortest AS path, the fewest number of hops, the path of least resistance, yeah? And so it goes, yeah? It will have a look at your code, it will have a look at the lowest med, yeah? Talking to a neighboring device. It will choose external BGP over IBGP. The admin distance, your routing systems use admin distance. The admin distance for external BGP is 20. The admin distance of internal BGP is 200. So 20 over 200 preferred. Then suddenly it starts, I wouldn't say to clutch at straws, but it's determined to choose a particular route. The path through the closest one, the path through the closest IGP neighbor. So now that is really using the IGP metric, yeah? And that OSPF would calculate. If that doesn't work, it will try the oldest route. Good heavens, I mean, one of them has got to be oldest, surely, yeah? And if that doesn't work, it will then choose the path that's got the lowest neighbor router ID. And if that doesn't work, I mean, as if you shouldn't have two of the same router IDs, I suppose. Or finally, the path with the lowest address. BGP is determined it will do something. Yeah, it will choose a route, come what may. Juniper's similar. Good heavens, yeah. If I just jump back, that is Cisco, because like I say, this is the Cisco proprietary one. But there's Juniper. Selects a path with a reachable next hop. Well, it's got to be there because that's the well-known mandatory. It has to be there. Then lo and behold, suddenly it goes on their version of the highest weight, a la Cisco. If that doesn't work, it goes on to the local preference. And so. Suffice to say that these things are determined to find a best route, and so they should. There it is, dudes, right? Here, the weight attribute, you can see here, it is specific to a device. We have set the weight 200 here. We look neighbor 10.1.1.1, neighbor 10.11.1, 10.1.1.1. The weight is 200. 172.16.1.1, the weight is 100. Highest wins. Consequently, the data will egress out of here. Well, then, of course, it might filter its way through, but that is how we can influence our updates. Fantastic. I just want to say again, this is local to a router. That is the weight. Here is the local preference. Now you can see here, look, right? We've got two edge devices talking to AS2, one talking to AS4, and they've got this baby on the inside. This is now going to talk to these devices. This local preference is 200 on this device, not on that interface, on that device. The local preference here is 100. Consequently, highest wins for local pref. Consequently, data will leave there, go to this one, and off it goes again. So the local preference is a preferred device local to that AS. AS path prepend. Good heavens. Well, data is egressed. There's an error in this slide. AS path, the data will egress here, and it goes this way. It's going to 172.16. Fine. So it leaves here, transits 2, transits 3, and hits 5. The return traffic from 5 will egress 5. There it is. It will transit 3. There it is. And it will transit 2. There it is. Whereas down here, it doesn't actually start in 5. There should be an error here, really, you know, or I suppose not one at all, just take it out, because the data here is egress in AS4. So, but if we go into that destination, there should be a connection. But the point is, the number of hops here, there's 1, 2, 3 in the AS path, and there's 1, 2, 3, 4, 5 here. BGP prefers the shortest path. Consequently, there it is. As simple as that. And there's the MED. Exactly as I said. Our system is talking to neighboring AS2, and we will set the MED. In this case, it's the lowest. This one has a configured MED of 200, which we have set. We are speaking to our neighbor, and we set that MED. And we also set this one. This is lower, and this is higher. So this will be our return path. These can be all configured in route maps. Yeah. So you could select certain data to take certain updates, to take the top link, certain updates to take the bottom. So your log sharing. Yeah. It is quite straightforward. It is traffic engineering. Yeah. Traffic engineering. You decide what you want to do. You say what I want to do. And the point is, you can influence outgoing traffic with the weight. It will choose the bottom interface or the top one, if there was one. It will choose, you could choose local preference from data egress in your system. Do I want to use the top router? Do I want to use the bottom one? That's up to you. So that is influence outgoing traffic, and this is influencing the returning traffic. And really, the biggie, no question, the biggest is the AS path prepend. You make the path appear longer than it is, so hopefully your data will return across the short one. And certainly the metric, because but that only applies to a neighboring AS, you know? Yep, they are. So how does this all come about? Well, you can see here, internal BGP, within an AS, we can't use wait. There is no point. Yeah, fine, we can't use it anyway, simple as that. But we could use local preference. They are carried within your iBGP updates. The metric and the AS path, they are carried within internal BGP metrics. The wait isn't. External BGP, this device is talking to this device. Again, the wait isn't carried because it is only local to a router, but you could choose that interface or another if there was one. The local preference is particularly relevant to to internal BGP. Consequently, it is not carried in external updates. Whereas the metric is, the multi-exit discriminator is, but it's only one hop. It will only go to this device. It is then stripped off. Whereas the AS path is sent to here, and it's sent to AS3, AS4, AS5, AS6, and life is good. The selection, we've already said. Certainly, there is the aggregation, yeah, because aggregation will give you a longer prefix. It would be chosen. Then, if that doesn't work, you could use the wait. If that is all equal between interfaces, you would then choose the local preference to select which device you want to choose from an egress from an AS. If they're the same, AS path prepend. If the AS paths are the same, use the metric, or you could use the metric. Yeah. Oh, good heavens. So, there is a quiz. Now, just bear with me a second here, chaps, because I want to show you something. If I drop that down now, and I go into here. Now, can you see my topology, Holly, or do I need to share it?
No, we're seeing that.
You see it here? Oh,
Yep.
Brilliant. Right, well, that is absolutely superfluous, because what I've done here, good heavens, it's nearly that time, isn't it? I didn't realize. Right, if I pick on this one here, right, the one called VIOS, there it is, I will open a link, I hope. And, right, it comes up like so. All right, these are Cisco devices. What I really want you to see is this. Show IP BGP. That will show the BGP table, chaps. All right, now look here. You can see here. The one we're particularly interested in is this one, because the others I'm not interested in. To be perfectly blunt about it. Oh, damn. Sorry, didn't mean to do that. As you can tell, show IP BGP. And there it is. Right, the thing I'm really interested in is this one here. 192.168.20.0. This is BGP. Yep, this is my BGP table. And it is telling you, look, if I move that out the way here, this is 192.168.20, this network over here, the one with the multi-layer switch, etc. And this device here, AS2000, can get to 192.168.20.0. That's the destination. It could go to a next hop interface of 200.116. 200.116 is that top link up there, right? I think. I'll just have a quick glance at that. Show IP interface brief. Right. So there we go. That's just about the same. 200.115 is 200.115 is the bottom one, actually. So if this is 200.115 on here, this one has to be 200.116. So, right, here, this one can go across 200.116. And you can see here, it's got a metric configured, yeah, which is the med. I just put that on just for fun. Look, so now these are your methods of criteria, yeah. Suddenly you've got the metric here, there. That's the med. You've got the local preference. Stupid as it seems, if they are the default value, you can't see them. Then you've got the weight, and then you've got the AS path. So now you can see that all of the data for 192.168.20.0 has been generated by a device in 65001. It has. And you can see it is originated from a network, from redistribution. It has, because I've done it. And you can also see this device can get to 192.168.20.0, going to 200.116, or it can go via 200.112, which is, of course, the top link. And that's the way it's going, because it has got this greater than sign. The greater than sign there is showing it's the best path. And there it is, look. There's my best path there. So this is the best path to that, yeah? Why? Because, well, the metrics are the same, yeah? The path is here, is shorter, yeah? But the weight was the same, the local preference was the same, they've all been redistributed, but this one has a shorter path. It's come from 65001, whereas that one, the bottom one, has gone through 3000. And sure enough, it does not. It's come through here. And that is how BGP works. I know it's just past that. Am I all right for about another minute or two, Holly, or do you want me to stop talking?
No, I think another minute, but I'm pretty sure these people have got places to be. So if we could
Fine. Right. Well, if I just do this, bear with me. I'll probably do it wrong now. Neighbor will say 200.1.1.6. Yeah, their weight 5,000. Good. Exit. Where are I? Do clear IP BGP. That's soft. Fine. Look, that's what I wanted to say, chaps. So now you can see here, look, I put the weight as 5,000 there. Suddenly, the weight is the first criteria. 5,000 is greater than 0. Consequently, the best route has now changed from 200.112. If I just scroll up a second, there, look, the best route there was 200.112 because of the shorter path, whereas now 200.116, higher weight, has overridden the shorter path. And that's how easy it is to influence BGP metrics. So after all that, BGP rules the world. Yeah, it is, you can get it to do anything, and it is eminently flexible. So there you go. I hope that's proved of interest to you all, chaps.